Welcome to lecture 3.9, the method of Frobenius. In the previous lecture, we saw a differential equation that was similar to a Cauchy-Euler equation, but it wasn't quite the right thing. So it didn't have a nice simple solution, but it had a solution that was a power series, and we learned how to find that and understand what that meant. So in this lecture, we're going to see the big unifying theory about when the power series method works and when it doesn't work. And we're going to see something a little more general, which is called a generalized power series. And I think you can think of this as a power series multiplied by a power of x. So take a power series and multiply it by x to the 1/2. That's a generalized power series. Okay, so let's get started with a quick review of power series. This is something that you saw in Calculus 2, and you learned it in a lot more detail in that class, and you're probably rusty on a lot of those details, and that's perfectly fine. I don't need you to remember or to be able to recall all the ins and outs of power series. I just want you to remember the main concepts, what they are. So let's go over those now. So a power series centered at x naught is it looks like this, but formally it's a limit of partial sums. So an infinite sum, what is that? Well, we take a finite sum, and then we keep adding more and more terms, and we see if that sequence converges. If that does, we say the limit exists, and the power series converges at x. Otherwise, it diverges. So here's two examples. So this power series, which we usually write it as n equals 0 to infinity of 1 over n factorial x to the n. So this thing converges to e to the x for all real numbers. And instead of converges, you're perfectly fine to think equals. This power series equals e to the x. In this class, that's fine. So if this is the real line, then every single point on the real line, if you plug in that point into here, you get e to the x. So we're going to say that equals e to the x. Now the next one, this power series, again, if you want to, you can get rid of this, and you can make this infinity. Now this converges to 1 over 1 plus x, but not for all x, only for x in this range. So if you draw the real line, this is 0, this is -1, this is +1, that's 1, and it's only going to work for x's in this range. So the reason why, well, this is actually a special case of a formula n equals 0 to infinity of x to the n equals 1 over 1 minus x. And this holds assuming that x is less than 1 in absolute value, meaning x is in here. It's clearly not going to hold for x equals 1. I mean, because then we just get 1 plus 1 plus 1 plus 1 plus, etc. So it's not going to hold at this point right here. And it's also not going to hold at this point here. Let's see why that is. Let's plug in x equals -1 into here. And if we do that, we actually get this thing. So in that case, we get 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus minus, etc. And if you look at the limit of partial sums, the partial sum is defined as the sum of the first n terms. So the first partial sum is 1. The second partial sum is 1 minus 1, 0. The third partial sum is +1. So the sequence of partial sums, so the sequence of partial sums is 1, 0, 1, 0, 1, 0, and this sequence diverges. So this is not going to this is going to diverge at -1, and this thing here, for the same reason, diverges at n equals +1. So that brings us to the radius of convergence. This is the largest number r, such that, well, I think the best way to see it is this example. So if your power series is centered at this point, you look at what interval around this point does this power series converge. So in this case, we say r equals infinity. This is a power series centered at 0, and everything converges. Whereas over here, it's a power series centered at 0, And things converge if you're less than a distance 1 away, if you're inside of this interval of radius 1. So we say r equals 1. So that is the radius of convergence, and here's the more general definition. Hopefully this will jog your memory just a bit. Now in Calculus 2, you learned all sorts of tricks about how to compute the radius of convergence, and when something converges, you learned about the ratio test, the root test, the comparison test, the alternating test, the integral test, and I don't know, there might have been 1 or 2 more. You do not need to know those in this class. You just need to know what a power series is, what it means for it to converge. That just means that this thing exists as a function. And you need to know what the radius of convergence is, and that's all, not how to find it. Okay, so we need a few more definitions. They're not as bad as they seem, trust me. A function is real analytic at a point if it has a power series at that point. So basically, remember Taylor's formula in Calculus 2? You don't need to know the details, but Taylor's formula said, here's a function, here's how you can construct its power series. And it involved the derivatives and the nth derivatives and n factorial. So think of, when you see real analytic, what you should think of is has a power series. So examples of something that is not real analytic at a point is f of x equals 1 over x is not real analytic at x equals 0. Because it's not defined at x equals 0. And in this class, the only time that things are not going to be real analytic at a point is when they're not defined. So really, when you see if a function is real analytic, in this class, that just means it's defined. Now, there are functions out there, really weird functions. I think the simplest ones are called bump functions. You're welcome to Google this if you want to. There are functions that are defined at a point, but don't have a power series representation. Taylor's formula does not work. They're weird. I think the best way to think about them, just if you're interested, is so there are functions that are like this, that are so flat at n equals 0 that every single nth derivative is 0. So the function is indistinguishable from the 0 function in terms of Taylor's formula, but it's not the 0 function. It's continuous and differentiable and so forth. Those functions exist. They're out there. You're never going to see them. Don't worry about them. For this class, real analytic just means it's defined. So this is not real analytic. Okay, so why do we care about this? Let's take a second order differential equation, something like this. You can divide through by the coefficient of y double prime. So even if there's an x in front of y double prime, divide that out and absorb that into p and q. So the point x naught is an ordinary point if p and q are real, if they're defined at x naught. So when it doesn't happen is when you have something like this. So otherwise, x naught is a singular point. Now, singular points come in 2 types. They could be regular or they could be irregular. And they're regular if both of these things are real analytic at x naught. I think they're defined at x naught. Okay, so let's do an example. Here's a homogeneous differential equation. So let's write this in this. Trust me, this is easier than this looks. Let's write this in this form. So in that case, p of x equals x squared, and q of x equals -4. And we're assuming that, and we're always going to take x naught equals 0 in this class. So is this function, so both of these functions are analytic at 0. They're defined at 0. You can just plug in 0. They work. So these things are analytic at 0. So in other words, this thing here is an ordinary singular point at x equals 0. Well, I should say at x equals 0. I should probably say, yeah, I said it. x not equals 0 is an ordinary singular point. Okay, so what's a non-example? What about the differential equation x y double prime plus y prime plus y equals 0? Looks harmless enough, right? Well, let's divide through by x. So if we do that, we get y double prime plus 1 over x, y prime plus 1 over x, y. So in this case, that is my p of x, and that is my q of x. Okay? Now here's the problem. These things they're not analytic at 0. They're not defined at 0. Again, in this class, it's the same thing. These are not defined at 0. So that means that x not equals 0 is singular. So is it a regular or is it an irregular singular point? Well, let's check. Let's check x, p of x, and that is 1, and x squared q of x, that's equal to x. That's what we had to check, this and this. And yes, these things are defined at 0. So this is a singular point, but it is a regular singular point. So this thing is a regular singular point. Let's do one more example. Suppose I had x squared y double prime plus y equals 0. So we write this in our standard form. This standard form, we'd make it monic. And we write this as y double prime plus 1 over x squared y plus 1 over x squared, sorry, my y prime and y equals 0. And now this is p and this is q. So this is px and this is q of x. And these things are also not defined at 0. So 0 is a singular point of this equation. However, in this case, check x p of x. Right away, that's 1 over x. That is not defined at 0. This is an irregular singular point. So x not equals 0 is an irregular singular point. And that's all there is to it. So just give it an equation, divide out to make it monic, and check these points and say, is 0 defined at these points? If so, it's ordinary. If not, it's singular. And then check these two things, xpx and x squared qx. And that will tell you if it's regular or irregular. Okay, so let's do a few more examples. This first one is called Chebychevs equation. This comes up a lot in physics and engineering. So let's write this in our standard form. This is y double prime minus x over 1 minus x squared y prime plus p squared over 1 minus x squared y. So we see right away that p of x equals negative x over, I'll write that x a little better, negative x over 1 minus x squared, and q of x equals p squared over 1 minus x squared. Now this thing here, we are going to write as negative, no, we don't have to. Actually, let's check. Plug in 0. You get 0 over 1, that's defined. Plug in 0 here, you get p squared over 1. Yeah, so actually we don't even have to do this, so let me write out that x not equals 0 is an ordinary point of this equation. And so just for fun, let's actually compute these things. So let's write this as negative x times n equals 0 up to infinity, 1 over, oh, not 1 over, I'm sorry, this is, what is this going to be? Okay, here's what I'm going to do. I'm going to write this in. So this is negative x times 1 over 1 minus x squared. And yeah, so that's going to be x squared to the n. And so that is going to be n equals 0 to infinity of negative x to the 2n plus 1. So this thing is only going to exist. This sum is only equal to this sum when we're in this interval. In other words, when x is less than 1 in magnitude. So this says that the radius of convergence is going to be 1. So similarly, Q is, I can write this as p squared times n equals 0 to infinity of x squared to the n, so x to the 2n, and this also has radius of convergence r equals 1. So even though x naught is an ordinary point, it's an ordinary point because these things are both analytic, they're both defined, we have to be careful because these things, which I write here and here, these are only defined as power series within this region, negative 1 to 1. So as it turns out, we'll see on the next slide that this equation is going to have a power series solution, but it's only going to be valid in this region, because it's certainly not going to be valid outside of this region, because this whole equation is going to break down in power series form out of this region, because this only holds in this region and this only holds in this region. So in other words, we're going to say that y of x is a power series n equals 0 to infinity of a n x to the n, but let's write that, but only for r less than or equal to 1. So the radius of convergence, maybe I said that a little funny, but only for this power series, this radius of convergence is going to be no more than 1, because these things only hold up in power series for at most 1. Okay, so that's this first equation. Let's do the second one. This is similar to what I did in the previous slide. So let's write this in standard form. Y double prime plus 1 over x cubed y prime plus y equals 0. We look at this and we say p of x equals 1 over x cubed. We say right away that p of x is 1 over x squared, and this is not analytic at 0. So this is not defined at 0. This is an irregular singular point at 0. So this is an irregular, I should say x not equals 0 is an irregular singular point. And it turns out the reason why we say it's irregular is when it's irregular, that's when the power series method is not going to work. So there is not going to be a solution of, we'll see this on the next slide, there's not going to be a solution like this because it's an irregular singular point. However, these functions are certainly defined everywhere else. So at x equals 1, x equals 2, x equals 3, whatever. So like, let's just take x not equals 1. That is going to be an ordinary point. And so as we'll see in the next slide, that means that if we wanted to, I don't know why we would, but if you wanted to solve this thing, you could certainly find a solution x minus 1 to the n. You could find a power series solution centered at 1 because 1 is an ordinary point. Now you would have to write this thing as a power series at x equals 1. That does not look very fun, but you could do it. Okay, so here's the main theorem of the section. And I've said a lot about this leading up to it, sort of hinted at where we were going, especially in the previous slide. So suppose we have a differential equation, second order like this in our standard form. So if x naught is an ordinary point, this is the first case, that means that p, q, and f have power series, but they might not be defined everywhere. P might be e to the x, it might be 1, but it also might be that 1 over 1 minus x, which has a power series something like x to the n, which is not going to be defined everywhere. So take the 3 power series, which we know exist, and take the smallest radius of convergence. That is the smallest radius that all 3 of these things are guaranteed to exist in. In that case, there's going to be a power series solution, and the radius of convergence of that solution is going to be the minimum of these 3 radii. So again, think of it like this. So let's suppose that P maybe exists in the whole real line. So in other words, our P is infinity. Maybe Q is maybe Q has radius of convergence. RQ. So maybe Q converges in this interval, and maybe F maybe converges in this interval. Well, that means we take the smallest interval, that's going to be this one, because this is the smallest interval in which all 3 of these things are going to converge. And in that interval, there will be a power series solution that will converge. So that's what happens when we have an ordinary point. And the way to think of it is there is a power series solution. When we have a regular singular point, so that means that this has a power series and all 3 of these things have a power series, we don't necessarily have a power series solution, but we have something very close. We have a power series times this thing for some constant r. And the same thing about the radii of convergence. You look at the 3 intervals in which they converge, you take the smaller one, and this thing is going to exist in that smaller one. So let me say a few words about what this looks like. So this is called a generalized power series. So one example of this is, let's suppose you have n equals 0 to infinity, a n x to the n, and maybe you have x to the 1/2. So what that means is, so you have a naught x to the 1/2 plus a1 x to the 3/2 plus a2 x to the 5/2, and so forth. So when you have a regular singular point, you might have solutions that aren't quite power series, but they're pretty darn close. It's like a power series multiplied by something else. Maybe this thing is r to the minus 2 times n equals 0 to infinity, maybe times bn x to the n. In that case, this is going to be a naught x to the minus 2 plus a1 x to the minus 1 plus plus a2 plus a3x plus a4x squared plus so forth. So these generalized power series, formally they look like this. I know that's can be kind of cryptic, but all it is, it's a power series multiplied by some x to the r. And r could even be complex. It doesn't necessarily have to even be a real number. But notice anytime r is a positive integer, that's a power series, or 0. So if this were to be x to the positive 2, we would shift these up by 2, but that's still a regular power series. So if x naught is an irregular singular point, then we, in general, don't have anything. So none of this is guaranteed, and that typically means that there is not going to be a power series solution. And honestly, I don't even know if there is a solution. I'm just going to say all bets are off. Okay, so let's do an example. Here's a differential equation, and we'll use this power series method. So first of all, let's write this using our standard form. So this is y double prime plus 1 over 2x times y prime plus 1 over 2x y equals 0. So this is going to be our p of x, and this is going to be our q of x. So this is, x equals 0 is a singular point because you plug in 0 and these are not defined. However, it's going to be a regular singular point because p of x equals 1/2 and x squared q of x equals 1/2 x. Both of these things are analytic at 0. They're both defined at 0. Okay, so let's use our power series method. Actually, let me say that by the theorem of Frobenius, because these things, because 0 is a regular singular point, there's not necessarily guaranteed to be a power series solution, but there will be a generalized power series solution. So that's going to be it's going to be a power series times x to the r. So let me write that as x to the n plus r. It's easier to put the n inside typically. So this is y of x. Y prime of x is going to be, n plus r times an times x to the n plus r minus 1. And y double prime of x is going to be n equals 0 to infinity of n plus r times n plus r minus 1 times an times x to the n plus r minus 2. Okay, so now as before, we're going to plug these things back into our equation. So let's do this term by term, this 2xy prime term. So I'm going to take this thing, I'm going to multiply by 2, and then I'm going to multiply by x, which is going to make this negative 2 into a negative 1. So let's do that. So this first term is going to be, let's see, so that's going to be n equals 0 to infinity of 2 times n plus r times n plus r minus 1 times a to the n times x to the n plus r minus 1. Okay, so this next term, this is y prime. That's just, this thing gets copied down here. So this is n equals 0 to infinity of n plus r times an times x to the n plus r minus 1. And then this last term, this is just y, that's just this term here. So that's going to be n equals 0 to infinity of an x to the n. This whole thing, n plus r, sorry about that. And this whole thing equals 0. So the game is the same as before. We're going to combine this into a single sum and set every coefficient equal to 0, because that generalized power series is going to be the 0 power series. Okay, so to do this, let's first of all factor out an x to the r. There's an x to the r in every term, and we don't need that. You may say, well, why was it there? Well, we will factor it out, but there's going to be an r. There's an r that lingers in these terms. So x to the r times n equals 0 to infinity. Now we have to add these two things together. How do we do that? So both of these are going to have an an and an x to the n minus 1. So let me go up here and do some math. So what is, let's see, so what is this term plus that term? How many n plus r's do we have? So we have one of them here, and then we have two n plus r minus 1 here. So that's 2n plus 2r minus 2 plus 1. Well, let's do this up here. So 2n plus r times n plus r minus 1 plus n plus r equals 2n plus 2r minus 2. So minus 2 plus 1 is minus 1 times n plus r. That's times. Okay, so that is going to be, I guess I switched colors without realizing it. I guess that's fine. 2n plus 2r minus 1 times n plus r times an times x to the n minus 1. And then this last term is going to be n equals 0 to infinity of an x to the n. And that equals 0. And we're going to divide through by x to the r. We don't need it anymore. But we do have these r's that are in here. Okay, so now the same thing as before. We want to combine these into a single term, but we have to shift the indices because we because we have an x to the n and an x to the n plus 1. So if we want to be formal about it, we could write, let's let m be n minus 1, and then n equals m plus 1, and we could substitute that in for each one of these like we did on the last lecture. But as I said in the last lecture, when you do this a few times, you get used to it, and you can just, in your head, substitute n plus 1 in for each n. So let's do that. So okay, so let's write this as a sum of n equals 0 to. Actually, you got to be careful. I think we might not be starting at 0. So let me do that. Let me take this term, and let me in place of n, let me put in n plus 1. Let's do that up here. So 2n plus 1 plus 2r minus 1 times 2n, sorry, not 2n, n plus 1, n plus 1 plus r. So now we can simplify this. So this is going to be 2n plus 2r, and then the plus 2 minus 1 is minus 1. So this is going to be 2n plus 2r minus 1 times that second term, this thing here, is n plus r plus 1. So n plus r plus 1. This is an a n plus 1 x to the n. Again, we're shifting everything up by 1. And now this next term is plus n equals 0 to infinity a n x to the n equals 0. So let's combine. Let's just combine these things. Oh, I forgot my sum. So we're starting at n equals negative 1 to infinity. So n equals 0 is the same thing as this m being n minus 1, which is 0 minus 1. So as before we had to shift it by negative 2, now we shift it just by 1. Okay, so let's combine these terms. So I'm going to write this as, oh, hold on. So before I can combine these terms, I can almost do it, but I have this extra n equals 1 negative 1 term here that I can't just come up, I don't have that term here. So I'm going to pick off that n equals 1 term over here, n equals negative 1 term. Let's do that. So when n equals negative 1, I get negative 2. So I get negative 2 plus 2r minus 1. Is that correct? Yeah, so I get 2r. But something is wrong here. What is it? Oh, I know what it is. I had a plus 1 here. So let's check this up here. 2n. This thing here should be a plus 1 right there, because I have 2 times. No, that's not right. That's definitely not correct. Or it was right the first time. What's wrong? Oh, I know what it is. Yes, here we go. So this thing here, this should be a plus right there. And let's show why that is. So this thing here is 2n plus 2r plus 2 minus 1, which is plus 1 times n plus r plus 1, right? Yeah, there we go. So that should be a plus. Something did not look right. There's our plus. Okay, now let's take the n equals negative 1 term here. So that this is going to be, so now we have 2r plus 1 minus 2, so that's 2r minus 1. N equals negative 1 gives me negative 1 plus r plus 1 is r times a negative 1 plus 1 is a naught. And then x to the this is just 1. No, sorry, x to the negative 1. That's x, yeah, x to the negative 1. And now, once I've picked off this n equals negative 1 term, now I can add these two sums together. And now I get n equals 0 to infinity of this plus that. So let me factor out my x to the n, and I get 2n plus 2r plus 1 times n plus r plus 1 times a n plus 1 plus a n, and now I'm factoring out x to the n. This whole thing equals 0. So this whole thing is 0. Notice I did not have this term here when we did regular power series in the previous lecture. And the reason is because we had the constant term, the x equals 0 term, and we took a derivative. That's a constant term. You get 0. You know, technically the derivative, okay, yeah, so technically the derivative of, let's do it, I don't even know if it's even worth doing this, dx of a0 x to the 0. Technically that is 0 times a0 x to the negative 1. So this but there's a 0 here, so we just ignore it. However, if r equals 1/2, so if the lowest term is a0 times x to the 1/2 in a generalized power series, you take the derivative, it does not become 0. It jumps right over 1/2 to negative 1/2, and so this term persists. So if this whole thing is the 0 power series, 0 generalized power series, this better be equal to 0. So this better be equal to 0. And this thing better be equal to 0. So when the first thing is equal to 0, so a0 does not have to be 0. That can be anything. So we cannot assume that that is 0. So that means that this thing has to be 0. So 2r minus 1 times r equals 0. This has a name. I never really call it this, but it's called the indicial equation. And DIC, this is not a word I think I've ever used in the English language outside of this application. So differential equations, and even in here I tried not to use this. So this is the indicial equation, and it tells us that r equals 0 or 1/2. Now this next one, this gives us our recurrence relation. So we set this equal to 0, and we get that a n plus 1, well, we can solve for this in our head, right? So this is, we get 2n plus 2r plus 1 times n plus r plus 1, and then I think on the top we get a negative 1 times an. So this is our recurrence relation. So things are a little bit different than the regular power series one. In the regular power series one from the previous lecture, remember we got an plus 2 in terms of an. So when we fixed a0, then we got a2, a4, a6, and so forth. We got the even terms. And when we fixed a1, we got the odd terms. Here, you get every term from a0. So you say, well, do we really have 2 degrees of freedom? We need 2 solutions, right? But that's where these arcs come into play. So we have 2 values for r. So when r equals 0, this is the first case. So when r equals 0, we have a generalized power series so generalized power series, this is something like, remember that? When plugging in r equals 0. And that makes it a regular power series. It's as if this thing wasn't here. So when r equals 0, we have a solution of the form y of x equals n equals 0 to infinity of a n x to the n. And the recurrence, let me take this recurrence and plug in r equals 0. And so we get that a n plus 1, let's put a comma there, equals negative. The bottom of this, when r equals 0, becomes 2n plus 1 times n plus 1 times an. So here, here's one solution. And then the other solution is when, how do I want to fit this in? When r equals 1/2. In this case, we have a generalized power series solution of n equals 0 to infinity of a n x to the n plus 1/2. And now the recurrence an plus 1 equals, so let's plug in 1/2 in for r here. So we get, so we 2n plus 2, because this is 1 plus 1, so that's 2n plus 2 times, here we have n plus 1/2 plus 1, so that's n plus 3/2. Plus 3/2, and then negative 1 times a n on top. So here's the solution that we get when n equals 1/2. And if you want to, you can plug this. You could take this x to the minus 1/2 out in front and make that a square root of x if you want to. So it's like it's a power series times the square root of x. So now, if you wanted to, let's finish by saying we have our two solutions. This is one of them. This is another one. So if you wanted to, you could write your general solution, y of x, as c0 times y0 of x. Say that's this power series. So plus c1/2 times y1/2 of x, where that's this power series. And this power series, if you wanted to, this second one, y of x, is, you can write this as the square root of x times n equals 0 to infinity of a n x to the n. So this thing here, you could pull the x to the minus 1/2 in front, write it like this. But so here's an alternative way to write the general solution. Again, I don't prefer this. Nothing else. It's a good way to think about it as these things being linearly independent solutions. But to solve this equation, we have two generalized power series solutions. One of them is this, and one of them is this. And this happens to be a regular power series, and this is a truly generalized power series. Okay, so I want to conclude this lecture with a word on some applications of what we've been doing to physics and engineering. There are a lot of models that come up in applied sciences that involve second-order differential equations and variable coefficients like the ones that we've seen. You've likely heard things like Hermite polynomials, Bessel functions, Chebychev functions, and these things come up because they were functions that were solutions to common equations that didn't have names. They had a power series form. So here are some examples of that. So Cauchy-Euler equation, well, we actually saw this a few lectures ago. The solutions we know are y of x equals x to the r. You can solve this using a power series method, and you will get those solutions back. You'll get things canceling a lot. And it's like what we did in the previous lecture when remember that lecture when we had the first power series example and all of the odd coefficients were 0 after n equals 3? It's going to be the similar case if you try to solve this using the power series method. Hermite's equation, this thing is used for modeling simple harmonic oscillators in quantum mechanics. I should say that Cauchy-Euler's equations come up when solving Laplace's equation in polar coordinates. And you will learn about Laplace's equation in the Series 7 lectures when we study PDEs. So wait a little bit for that. That'll come back. Legendre's equation, that's this thing. So P is a parameter. This is used for modeling spherically symmetric potentials in the theory of Newtonian gravitation and electricity and magnetism. I don't know much about this. It's been a long time since I studied physics. But one example I can come up with is it's like the wave equation for an electron in a hydrogen atom. This equation models it. That's all I know about this, honestly. Bessel's equation, I do know that this thing comes up a lot for analyzing vibrations of a circular drum. Similar to this one up here, when you take a standard PDE that we're going to learn about, the wave equation, and put it into polar coordinates, this is what we get for one of the boundary value problems. Airy's equation models the refraction of light, and Chebychev's equation arises in numerical analysis techniques. So these things that you've been studying, these do come up a lot in a lot of applications in physics, engineering, and applied science.